Hi Year 10, here's the third video for our topic of logarithms. In this video we're going to look at log graphs. So far in this series of videos we've learned how to define logarithms, how to switch between index form and log form, and then in the last video we learned about the log laws, the change of base rule, and how to use the calculator. So we're going to start with inverse functions. Inverse functions undo one another. Now we're going to do an entire topic on this, so this is just a brief introduction. So let's have a look at these two functions, y equals 2x take away 1 and y equals x plus 1 all divided by 2. So these two are an example of inverse functions, but there's an easy way to test. What we do is we just substitute a number into the first equation, so x is equal to 4. Then we take our output and substitute it into the second equation. If we end up where we started, then they're inverse functions. So let's have a go. So substituting the 4 into here, we get 2 lots of 4 is 8, take away 1 is 7. Now I'm going to take my 7 and substitute it in here in the second equation. So I'm going to get y is equal to 7 plus 1 all divided by 2 is equal to 4. So because I started at 4 and ended at 4, these two are inverse functions. And here's a little diagram to help you understand. So here we've got two function boxes, the function itself and the inverse function. And we've got apples going into the function and then they turn into lemons. And then we take the output of the function and put that into the inverse function and they end up back as apples. So another interesting thing with inverse functions is that if you graph them, they are actually reflections of one another over the line y equals x. Again, we're going to look into that in more detail in the video on inverse functions. So you're probably wondering what on earth this has got to do with logarithms. Well, we learnt in the very first video that logs and indices are inverse relations. They undo one another. And similarly, y is equal to log base 10 of x and y is equal to 10 to the power of x are inverse functions. Let's use our test and see if it's correct. We're going to substitute x is equal to 100 into the first equation. That means putting the 100 in here. So log base 10 of 100 is 2 because 10 squared is 100. Now we're going to take our output and put it into the second or the inverse function. And we get y is equal to 10 squared, which is equal to 100, which is what we started with. So yes, they are inverse functions. And so that means that the graph of log base 10 of x and 10 to the power of x are going to have the same shape, but they're just going to be reflections of one another over that line y equals x. So let's start with the graph y equals 10 to the power of x. Okay, it has a y-intercept at 1, and it has a horizontal asymptote at y is equal to 0. Now when we reflect that over, these things swap. Have a look, we've got now an x-intercept at 1 and we've got a vertical asymptote at x is equal to 0. So this is our graph, y equals log base 10 of x. Note how it's not defined for negative values of x. Now similarly, the graphs of y equals log base 2 of x and y equals 2 to the x are also reflections of one another over the line y equals x. We can see that again. Here we've got the y-intercept of 1 becomes the x-intercept of 1 and the asymptotes switch as well. And that's pretty much going to be the same with any log and its corresponding exponential. So where the bases match, they're always going to look like that. The only thing that's going to change really is the dilation or how steep it is. And we'll go through that in the next slide. So just like other functions, log functions can be transformed. We've done a little bit of this when we've looked at quadratic relationships, but we're going to do an entire topic on transformations as well. So again, this is just an introduction. So suppose I take this really complicated function here, y is equal to a log base b of x minus h in brackets plus k. What is the effect of each of those constants, a, b, h, and k, on the basic log graph? Right, we just talked about changing the base, didn't we? We said that's going to change the dilation or how steep it is. That's also the case with A. It's a different change, but we're not going to go into that at this stage. So both changing the base and putting in a different number out the front is going to change the steepness of the graph. Now, if I bracket a number with the x, that's going to cause a horizontal shift. And if I add or subtract a number from the end of the graph, that's going to cause a vertical shift. So let's look at a couple of examples. So we're going to consider the graph y equals log base 2 of x. There it is there. So we want to graph log base 2 of x plus 1 on top of it. Now this is the easiest of the transformations where we just add or subtract a constant from the end of the function. All we have to do there is take that whole graph and shift it up 1, like this. And there's our new graph. Y is equal to log base 2 of x plus 1. Okay, how about if we want log base 2 of x minus 2 in brackets? So in this case, this is going to be a horizontal shift, and it's going to shift it 2 places to the right, so over here. Now people do get confused with this. They don't remember which way to go. One way to look at it is it shifts over to what makes 0. So it shifts over to 2. So we take our normal 0, which is the asymptote in this case, and we shift that over 2. So there's our new asymptote. And finally, 2 multiplied by log base 2 of x. And so this is going to change the dilation. So it's going to swivel it around like this. Okay, changes the steepness. Now, the best way to learn about graphing is to use this program called Desmos. It's free for anybody to use. You don't even need an account. Just Google Desmos and then go into the calculator. You'll see this screen. On the right-hand side, you've got graph paper, and on the left-hand side, you've got a place to enter your functions that you want to graph. So we're going to want to graph a log graph. We're going to choose log base 10 because we don't have to put in the subscript, although I'll show you how to do that later on. So there's our graph. It's drawn it for us. Now, we can use 2 fingers to zoom in, like that, or we can zoom out, and using 1 finger moves it left and right and up and down. Okay, now that's all very well, but not very interesting or helpful. The powerful thing about Desmos is the use of sliders. So if we type y is equal to log, spell it right, log x, and then add c, it's going to come up and ask if I want to add a slider. So it's recognizing the c as a constant, and I do want to add a slider. By default, it's going to be set between -10 and +10. That's probably a little bit too big, so let's change it to -5 and +5. Now have a look what happens when I set this off. What's it doing to the graph? It's moving it up and down the y-axis, isn't it? And that's the effect of adding a constant to the end of a function. So that's our very first transformation. It's a vertical transformation. Okay, second transformation. So in this case, we're going to bracket the constant with the x, and we always put that in as a negative, so x minus c. Again, it goes between -5 and +5. That's fine. All right, what's happening now? This one is a horizontal transformation, isn't it? It's shifting it left and right. So when it's positive, it's going to the right, and when it's negative, it's going to the left. All right, now let's have a look what happens when we change. We want to do it here. Constant in front. So we'll just put that as x there. Now in this case, I'll just start this at 0. I think we won't do the negatives yet. What's going to happen here? It's changing the steepness of it. It's not just swiveling at about that point. You see that it changes the shape. So it's changing the steepness, or it's called the dilation, actually. All right, let's put the negative in and see what happens. You may know this. What happens when I put a negative in front of a function? Okay, so it flipped over the x-axis. Did you see it do that? Here it goes again. So changing the steepness, and when it gets to 0, it flips over and becomes negative. Great. All right, 1 to go. So we need to change the base. I'm going to get rid of this slider. Now in this case, we want to type in y is equal to log base 2, suppose. What we've got to do is hit shift and underscore to get. Did you see how it dropped down then? And now I want the right arrow to get out of there. So I want an x here. And there's y is equal to log base 2 of x. Again, it's changed the dilation. But we don't want a 2 there. We actually want a slider. So let's put c in and add our slider. Now have a look at this. This is curious. What happens for negative numbers? Disappears. Did you see that? Doesn't actually exist, which is true, isn't it? We can't have a negative base. So let's start this at 0, and we'll go up to 5, and we'll have a look what happens. Okay, so again, it's changing the dilation. It does a curious thing. Do you see it? It flips over the x-axis even though it never goes negative. What sort of numbers does it flip over the x-axis for? Let's have a look at them. Here they come. They're numbers in between 0 and 1. In fact, do you remember it's not defined for bases of 1? Let's see if we can find 1. There it is, disappeared. Okay, so in between 0 and 1, it acts like a negative, flips over, a negative in front of the function, it flips over the x-axis, and greater than 1, it's just normal, changes the steepness. I'm going to have a look on the next slide why that happens. So what is the deal with this graph? Y is equal to log base 0.5 of x. Okay, let's have a look at it algebraically. So I'm going to turn this around into index form. I'm going to write this as a half. So half to the power of y is equal to x. Now I can write a half in index form as well. That's 2 to the negative 1. When I raise a power to a power, I multiply those powers. So 2 to the negative y is equal to x. Now let's put it back in log form. So it's going to be negative y is equal to log base 2 of x. Can you see where this is going? Let's bring this negative over. Y is equal to negative log base 2 of x. These two graphs are identical. That's why it flips over, because it's exactly the same as having a negative out the front. All right, let's have a look on Desmos. So here's our graph y is equal to negative log base 2 of x. It's red. You can faintly see it there. And there's the graph y is equal to log base 0.5 of x. That's the blue one. So they're the same graph. So that brings us to the end of this video. In the next video, we're going to look at equations and how to solve them using logs.